Hey guys, welcome to yet another video. Today I'm gonna talk about Ant-Man. That's right, one of my all-time favorite Marvel superheroes. As you can see, what's his superpower? He can be so small. All right. So in this society we live today, so how's it like to be small? Okay. If you haven't watched Captain America Civil War, go catch it because even with a multi-million dollar state-of-the-art attack suit like Iron Man, if you're as small as Ant-Man, you can actually cause a lot of damage, okay, by pulling out wires, getting into his systems and all that. All right, so pretty cool, pretty cool. Okay, where am I going with all this? All right, so basically today we're going to talk about the kinetic model of matter. Okay, so what is kinetic model of matter? It's basically a theory on the study of particles where you look at matter in the smallest form. So just like Ant-Man, you are going into the smallest form so that you can actually see all what actually constitutes all matter, be it a solid state or liquid state or gaseous state. Okay, so by studying that, you can see how the particles actually behave in the different states of solids, liquids, and gas. Okay, so one of the overlying assumptions for kinetic model is that you actually assume that all matter, like what I mentioned earlier, is made out of many particles, small particles that are always in continuous random motion. Okay, you may say, hey sir, this doesn't seem to be in continuous random motion. Well, look again. You can see actually the particles are vibrating. Can you see that? Right? So they are basically just vibrating about at fixed positions. Okay, so let's see what I'm gonna do. What do I have here? I got ice cubes in a cup and a container here. If I were to pour it over, boom, let's see what happens. Okay, my ice cubes actually go into the cup. Does it actually fill up the shape of the container? Nope, not really. You can see still pockets of a space over here. Okay, so basically solids, they actually have fixed shape and fixed volume. It doesn't really take up shape of any other container. Okay, what about liquids? You can see, oh, liquids, the particles are still very close together, but it seems to be in a random arrangement, no fixed arrangement like what you saw in solids over here. You can see they are more or less in the rows and columns, so pretty fixed here. But in liquids, you can see it's actually basically sliding around, right? Okay, but are they still close? Still pretty close together. Yep. So what happens if I were to pour it in and whoosh? Let's check it out. Is it? Oh yes, it actually takes up the space of the container, right? So it doesn't really have a fixed shape, but more or less has a fixed volume because whatever volume here I pour here will have the same volume. Okay, what about gas? Okay, we to add heat to it and boom, change it to gas. Okay, oh, you can see compared to solids, compared to the molecules in solids, the molecules in liquids. What can you say about the molecules in gas? They're actually moving much faster, right? All right, you can see whoosh over here, right? So, if I want to pour it into my container, do you think it will actually take up the space? Okay, let's check it out. Okay, I got a cover here before I pour it. Open the cover. Oops. Oh, what's happening here? All right, it actually flew all the way out. Okay, what actually happened? Why didn't the gas move in? Oh, because when I open up the lid, the gas actually doesn't really have any fixed volume. It actually takes up whatever volume you're giving it. In this case, I'm not shifting. You see, I actually covered the cup initially, right? So, although I covered the cup initially, but when I pour it out, I actually remove the cover, so I'm actually the volume that I'm exposing the gas to is not just the container, but the entire atmosphere, right? So, gas basically no fixed shape, no fixed volume. All right. Okay, so just quick recap. Basically, in short, we are looking at solids, liquids, gas. You can see here the property for solids will be fixed shape and fixed volume, incompressible. For liquids, basically only fixed volume only. Incompressible, that means the shape, there's no fixed shape. You can put it in a container, you can put it in a cup, it will take whatever shape of the cup. Okay, whereas for gas, okay, no fixed shape, no fixed volume. Basically, whatever volume, remember I open it up to the atmosphere, it actually spreads itself out to the whole room. Okay. Okay, so next we look at the molecular structure. As you can see, molecular structure of all the solid particles are actually more or less in quite neat rows. So they're actually and they're also very close. So very close and regular pattern, neat rows, very little space in between. Similar for liquids, okay, very little space, but they are not really in rows and columns, but in some random arrangement, very little space also. But for gas, they are far apart and random, okay, with lots of space in between. Okay, what about intermolecular forces? Okay, for both solids and liquids, they are strong, very strong, especially for solids. But for gas, they are very, very weak. Okay, which is the reason probably why they are not really being held back. So in a container, if I remove the lid, since the molecular forces are so weak, the gas will actually come out of the entire glass, right? It will actually move all over. Whereas for solids and liquids, even I to remove the lid or leave the lid on, the solid cubes of ice or the liquid, the water will still remain in the glass. Okay, the final part, we're going to talk about motion. All right, remember at the start of this topic, of this video, we talked about the kinetic model of matter. So what's kinetic model of matter? Is basically the study of all matter by looking at the smallest particles. Just like Ant-Man, you go very small, you look at all the particles, and these particles, the assumption is that all particles are always in continuous random motion. Yes, you at the corner. I know you're asking this question. Yes, I know liquids are moving, gas particles are moving, but solid particles aren't really moving, right? Hey, look carefully, man. If you look really carefully, I'm gonna share with you a secret. Can you see that? That's right. They are basically vibrating about fixed positions. So even though they got regular patterns, but they are still moving, just that they are vibrating at their positions. Okay, so just like in the army fall in position, they are all in the same position. Okay, but for liquids, slide past each other, okay, because they are still very close. But for gas, oh, they fly past, moves at very high speeds. All right, so okay, for this entire chapter, just one last part. As you can see, solids, liquids, gas. Which one has got the highest temperature? That's right, for gas, lowest temperature solid, as you heat it up, it melts, it becomes liquid. You heat it some more, it becomes steam, as in gas, right? So, more heat, the higher the temperature. You can see it actually moves what? Moves faster, right? You can see here, it moves a little bit, vibrating at this position over here. Starts to move around the friends, and then over here, oh, it moves around the whole classroom, right? Okay, so as you add in more heat, you give it the higher temperature, the kinetic energy of a particle increases. Okay, so that's all I want to share with you about this topic. Hope you found this video interesting and you learned something. Okay, I'll see you in the next.